Okay, so in this class, we'll be looking at classification of matter. Recall that in our previous class, we said that chemistry study matter in relation to the composition of matter, the properties of matter, and the changes that matter undergo under different conditions of temperature and pressure. So this matter we are talking about, which is of course anything that has mass and occupies space, meaning almost everything around us is a matter. We have classified matter into three classes. Matter may be an element, it may be a compound, it may be a mixture. And these are the three groups in which matter can be classified: elements, compounds, and mixture. So, what is an element? An element is a substance which cannot be split into simpler units by an ordinary chemical process. A simple substance or the least classes of substance. And so because it's so simple or because it's so small, you cannot split it into simpler units by an ordinary chemical means. So at the time of writing this, there are about 118 known elements to man. So these elements are usually arranged in a table called the periodic table. So right now, known elements in the periodic table are 118 of them. And these 118 elements are again classified into three groups. We have the common one like iron, tin, gold, oxygen, iodine, as well as the unfamiliar one like the radioactive ones like rubidium, actinium, and xenon. All of these are examples of elements. And so these elements are classified again into three classes. We have some groups that are called metals, you have non-metals, and you have metalloids. These are the three groups of elements: metals, non-metals, and metalloids. Now, how do we distinguish this group from one another? A metal is any element that ionizes by losing electron. An element that ionizes, that is becoming an ion by losing an electron. Now, what does it mean to become an ion? Elements in their natural state are usually neutral, but sometimes condition may happen that they can become charged particles, and those charged particles will be negatively charged or positively charged. Now, the process of becoming charged particle is what we call ionization. The process of becoming a charged particle. That is when an element loses an electron or gains an electron to become a charged particle. That process is called ionization. There are a group of elements that become ions by losing electrons. There are some other ones that become ions by gaining electrons. Metals are those that lose electrons to become ions, while non-metals are those that accept electrons to become ions. For example, sodium is an element and it is a metal. It's a metal because it ionizes by losing electron from the outer shell to become a sodium ion. Sodium in its natural or neutral state is written with the symbol Na. In this case, for sodium to become an ion, one electron has to be lost from the outer shell. And once that electron is lost, sodium now becomes a charged particle like sodium ion. And then the electron that is lost is this E minus. In its natural state, it has 11 proton and 11 neutron. But the moment it ionizes, one of the electron, 11 proton and 11 electrons, once it ionizes, one of the electrons is lost. Recall that the number of electrons is always equal to the number of protons, and electrons are negatively charged, while protons are positively charged, so that sodium in a neutral state is neutral because the charges, the negative charge of electrons cancels the positive charge of proton. That is why in a neutral state, all elements, the atom of elements, they have no charge. But the moment they become ions, electron is lost again. In the case of metals, electron is lost. Why not metals? Electron is gained. So metal basically a what? Element that ionizes by losing electrons. Other examples include magnesium, Mg, represented by Mg in the symbol. When it ionizes, two electrons are lost from the outer shell. So they'll have Mg, 2 plus, that is, the 2 plus here signifies that two electrons were removed, and the two electrons removed representing with two E minus. Now, where is this electron being removed from? The outer shell of the element in question. Now, when we come to electronic configuration, you understand better. Or let me digress there quickly. Sodium, let me start with this sodium, has one electron in the outer shell. The electronic configuration of sodium is something like this. It has two electrons in the inner shell and eight in this other shell, the next shell to the inner one. Now it's 10 altogether, while the outer shell has only one electron. So whenever it ionizes, this outer electron is lost. And when that happens, the number of protons is no longer equal to the number of electrons. That is why, because of the excess proton, that is why we present the ion with Na plus to show that the number of protons, because protons are positively charged, the number of protons is now more than the number of electrons in a charged sodium ion. That is the meaning of that. The same thing is applicable to magnesium. Magnesium is atomic number is 12. That means it has two electrons in the outer shell next to sodium. So when it ionizes, these two outer electrons are removed. And when that happens, number of protons is no longer equal to number of electrons. Proton now is two more than electron because it will remove two electrons. So that it now become a charged magnesium ion with excess of two protons. So any element that behave like this, that is by losing electron to become an ion, is a metal. Non-metals, on the other hand, gain electron to become an ion. A perfect example is chlorine. Chlorine has 17 electrons. That is, the atomic number is 17. And because the number of protons is equal to number of electrons. So chlorine in its neutral state has no charge because the charges cancel out. Proton is positively charged while electron is negatively charged. So if the numbers are equal, then the charges will cancel out. So this is configuration of chlorine that I'm drawing. This is 10 electrons altogether. Then the outer shell has 7 electrons since the atomic number is 17. So if I have 10 in the inner and the next shell, the remaining 7 will go to the outer shell. This is 4 now, 6, and then the seventh one. So whenever chlorine ionizes, because it cannot remove all these 7 electrons from the outer shell, there's something we call octet structure. Octet structure is an atom of element having 8 electrons in the outer shell. And this octet structure is configuration for stability. In other words, for an atom to be stable, it must have 8 electrons in the outer shell, or 2 in the case of helium. It's only helium that has 2. Every other one, for them to be stable, they need 8 electrons in their outer shell. So chlorine that has 7 already needs only 1 to achieve that configuration of stability. And so it's not going to lose all these 7, rather, it's going to collect from anyone that is willing to donate to it. And of course, something like sodium that is losing 1 electron can easily donate this 1 electron to chlorine. And that is why there is usually a reaction between sodium and chlorine, because sodium is willing to donate 1 electron, chlorine is willing to accept 1 electron. So when chlorine accepts such an electron, the number of electrons now becomes more than the number of protons. So chlorine is negatively, the chloride ion is negatively charged once it receives an electron from sodium, for example. So non-metal accept electron and then they become negatively charged, while metals lose electron and become positively. And metalloids is a group that share both the properties of metals and non-metals. Now, in other words, they can neither lose or gain electrons depending on the condition of reaction. So, and we have, I think, 3 of such metals, that is, such element rather, 3 of such elements: silicon, germanium, and then what is that third one again? There are 3 elements that behave like that, like sharing the properties of metals and non-metals. We have silicon and we have germanium. They can behave as both metals or non-metals, and that is why we call them metalloids. Okay? So in summary, metals do what? They ionizes by losing electron, while non-metals ionizes by gaining electrons. Now, differences between the physical properties of metals and non-metals. In our previous class, we talked about properties of matter. Maybe physical properties or chemical properties. Because that when we say properties in chemistry, we are not talking about the belonging of something, rather we're talking about the behavior or the character of that thing. So when we say properties here, the properties is talking about the changes that matter undergo. And recall that changes could be physical changes or chemical changes. So now we talk about the differences between the physical properties of matter, of metals and non-metals, right? Differences between what? The physical properties of metals and non-metals. Then metals are malleable. That is, you can hammer it and turn it to any desired shape. That is the meaning of malleability. All metals are malleable. You can hammer it and what? Turn it to a desired shape. Like a blacksmith. When you go to a blacksmith workshop, you see the first of all heat up a piece of metal and they use it to construct or design whatever object they are interested in. You can't do that to a non-metal. You take a wood and hammer it to trying to convert it to a different shape. So that wood is going to break. I'm not talking about wood carving. When you say malleable, it has to be hammering. You cannot hammer a wood or plastic to turn it to a desired shape. It's only metal that you can do that to. So malleability has to do with the ability of something to be hammered and converted to a desired shape. So metals are malleable, while non-metals are non-malleable. Also, metals are ductile. Metals are what? Ductile. Ductile has to do with ductility, has to do with the ability to stretch a material and turn it into a wire. Now you can stretch a metal to any length and turn it to a wire, something like a wire. You can't do that to a non-metal. Wood, for example, you can't stretch a wood. You may have a bar of iron like this, and then this bar of iron can be heated, can hammer it and stretch it to a very long iron rod or to even a tiny wire, like the iron, those round iron bar we use as a reinforcement in construction industry. Some of them are made from bars of iron or even iron scrap, and that is done by melting the metals and then molding it to a desired shape, either a wire or a rod. So that ability to convert a metal to a wire is what we call ductility. As metals are ductile, they can be stretched into wire. You can stretch a non-metal to form a wire. So the differences here is what? Metals are ductile, non-metals are not ductile. Another one is metals are sonorous. When you say something is sonorous, it means when you hit that thing with another metal or with any object or with a stone, it produces a kind of melodious sound. For example, if you have any metallic pole around you and a wooden pole around you, take a stone or another piece of metal and hit that metal or that pole, the metallic pole, also hit a wooden pole. You see that the wooden pole will produce a dull sound, while a metallic pole will produce a kind of echoing sound. That kind of echoing sound, that sound kind of melodious, is what we call sonorous. So non-metals are what? Non-sonorous, while metals are sonorous. When you hit a metal with a stone or with another metal, it produces a sonorous sound, a kind of melodious sound. Non-metals don't do that. They produce dull sound. And so they are what? Non-sonorous. Metals are what? Good conductors of heat and electricity. When we say conductor in physics and chemistry, I don't mean the first conductor. Rather, I mean something that allow electricity to flow through it easily. So a conductor is what? Something that allow the passage of heat and electricity, allow heat and electricity to pass through them. The metals are what? Good conductor of heat, electricity. Why non-metals are non-conductor? or poor conductor. Let me not say none because there is an exception, which is graphite. Graphite is a non-metal, but it's a good conductor of electricity. So metals have great tensile strength. Metals have great tensile strength. There is the ability to withstand a lot of load or pressure. When you put a heavy load on metal, it can withstand that load. Then put the same load on a non-metal. The non-metal may not be able to withstand it. The strength of a metal is far, far more than the strength of a non-metal. Metals can withstand a lot of pressure, a lot of tension. This tensor is from the word tension. Tension. And if you construct a bridge, the weight that the metal will hold is far, far more than the weight that the non-metal will hold. So tensile strength has to do with the ability of the material to withstand a lot of tension. The tension that a metal can withstand is far, far more than the tension that a non-metal can withstand. So we say that strength, why non-metals are brittle, that is, they are soft, and so their tensile strength is poor or low. Metals are lustrous. Metals are lustrous, that is, they shine. They have that shining ability. Most of them, also, they are lustrous in nature, and they can shine brightly. Why non-metals are non-lustrous and do not shine. The metals have high melting and boiling point, while non-metals except carbon have low melting and boiling point. I would say melting point of an object is the temperature at which it changes from solid to liquid. So if I have this is a material here, and this happens to be a metal, and this is another material, same size, but this one is a non-metal. Then both of them are solid, and I want to convert them to liquid because to do that, I need to apply heat to melt them. So I will apply heat on this metal until the temperature reaches the point that can break the force of attraction between the particles of this metal. Until that force of attraction is broken, before this metal can turn to liquid. And the amount of heat needed to achieve that is far, far greater than the amount of heat needed to turn a non-metal to liquid. That is what that point is saying, that the melting point of metals is usually high, while that of non-metal is usually low, with the exception of carbon. Also, the boiling point of metals is usually high than the boiling point of non-metals. Now, when we say that, how can metal boil? Yes, metal can boil. You know that there is a liquid metal. Mercury, for example, even though it's a metal, but it's in liquid form. Now, apart from mercury that is in liquid form, when you heat up a solid metal, a piece of metal, most metals are solid at room temperature. But when you heat them up to a certain temperature, they become liquid. So to boil that liquid, you need to apply more heat. That is what we are saying here, the boiling point. Okay? So mercury is in liquid form. If you have to heat it up in order to boil it, the amount of heat needed to achieve boiling will be far, far more than the amount of heat to boil a non-metal. And metals have relatively high density. The density of material is the mass per unit. One analogy that I love to use in my class with my students. Let's assume I have a cup or two cups of the same size. This is cup A. And in this cup A, I have pieces of iron filings. Iron filings are those pieces of iron that drop whenever we use a saw to cut iron. You go to any welding shop where they cut irons a lot. Those pieces of iron that used to drop when the cutting is being carried out. We call them iron filings. Iron filings. So let's assume you pick those pieces of iron and you put the pieces of iron in this cup. Then you have another cup of the same size. The same size. And in this second cup, you have maybe powder in this cup. They are the same size. Then you fill them with different things. This cup B. Which of these two cups do you think will be heavier? Of course, cup A will be heavier than cup B. The question is, why is cup A heavier than cup B? Because the density of iron is more than the density of powder. And what is density? In literal or in layman language, The density is a measure of how heavy or how light an object is. But scientifically, we define that as what? Mass per unit volume. The mass of an object is the quantity of material used in making that object, while the volume is the container that contain that very thing. So now these two things, iron filings and powder, the container here are of the same volume, but the masses of material in iron is far more than the masses of material in powder. That is why the cup A containing iron filing will be heavier than the cup B containing powder. So in essence, metals have what? High densities, while non-metals have low density. Okay, that is that for differences between metals and non-metals in terms of their physical property. What about in terms of their chemical property? For chemical properties, when we say chemical properties, we are talking about the type of reactions that these elements undergo. For metals, they are reducing agents. And what do we mean by reducing agent? A reducing agent is something that brings about reduction. Now, what does it mean? Okay, when we say reduction, let me define that word first. Reduction in this case means there are three definitions, but we are concerned with one of the definitions for now. But let me give out the three definition first. So reduction will be removal of oxygen, addition of hydrogen, or decrease in oxidation number. Decrease in what? Oxidation number. The last one is what we are interested in for now. Now, decrease in oxidation number. Now, we are saying that metals are reducing agent. In other words, they cause other things to decrease in oxidation number, while they themselves are oxidized in the process. Because we said that a metal is anything that ionizes by losing an electron. So once they lose electron, for example, sodium, before it becomes an ion, it has to lose one electron from the outer shell. And when it loses an electron, it becomes a sodium ion. And the electron that is lost is this one. Here, when sodium is in neutral state, the oxidation number is zero. That is, the oxidation number of an atom in its neutral state is zero. But the moment it loses an electron, the oxidation number has increased to what? Plus one. This plus here means plus one. So from 0 to 1, that is an increase. Okay? But we are talking about reduction for now. We say metals are what? Reducing agent. How do they reduce? Chlorine is accepting this electron lost from sodium. So when chlorine accepts that electron, it becomes a chloride ion. Chloride what? Ion. Now chlorine in its natural state or in neutral state, the oxidation number is zero. But the moment it accepts electron from sodium, the oxidation number becomes minus one. From 0 to minus 1, of course, 0 is bigger than minus 1. That is negative 1. 0 is bigger than it. So from 0 to negative 1, that is a decrease. Decrease in what? In oxidation number. Decrease in oxidation number. Now, what brought about this decrease in oxidation number? It is because sodium is giving out one electron to chlorine. And that is why we say metals are reducing agent. They, they are the one bringing about reduction because they are losing electrons. As those electrons are lost from metals, there must be something to accept the electron. And that thing that accepts the electron, the oxidation number of that thing will decrease. Decrease in what? Oxidation number. That is why we say that metals are reducing agent because they are the one donating electron. As they donate the electron, the non-metal accepts them, then the oxidation of the non-metal decreases from 0 to negative something. Hmm? I hope that explanation is clear enough. So metals are reducing agent. In other words, they bring about what? Reduction. Why they themselves are oxidized. Now, what is oxidation? Oxidation is addition of oxygen. That is the opposite of this. Addition of oxygen, removal of hydrogen, and increase in oxidation number. Let me write it down also. It's very important. Oxidation, addition of oxygen, removal of hydrogen, and increase in oxidation number. Increase in oxidation number. Okay, so we are saying that metals are what? Reducing agent. No metal are oxidizing agent. Now, what is oxidation? The last definition here is what we are interested in, increase in oxidation level. Using this same example here to explain it. Why are non-metals oxidizing agents? Because they are bringing about oxidation. Oxidation. Before sodium loses an electron, it cannot just lose electron randomly. There must be something willing to accept that electron. And that thing that is willing to accept that electron is non-metal. So for sodium to lose electron, there must be a non-metal present to receive that electron. So the non-metal is bringing about that oxidation, which is increasing the oxidation number. Now, when sodium is to plus one, that is the oxidation we're talking about. What brought about that increase in oxidation from 0 to plus 1? It is because of the presence of non-metal that is willing to accept the electron that is being lost from sodium. That is why we say non-metals are what? Oxidizing agents. That is, they tend to ionize by gaining electrons to form anions. Okay, and because they are oxidizing agents, they themselves are reduced once the oxidation takes place. And another difference is about metals form basic oxides with oxygen, while non-metals form acidic oxide, something like calcium oxide or sodium oxide, magnesium oxide. All of this can dissolve in water to form base. They would say that metals are what? They form basic oxide, while non-metal form acidic oxide with oxygen. That is, when non-metal combine with oxygen, they form acidic oxide. Acidic because when they dissolve in water, they can produce acid. Example is carbon dioxide. When carbon dioxide dissolves in water, can form that is formed triisocarbonate for acid. So because of that, we call it acidic oxide. So metals form what? Basic oxide, while non-metals form acidic oxide. Okay? Some metals or some reactive metals, not all, some reactive metals can displace hydrogen from acids. That is, whenever such reactive metals of acids, we can displace hydrogen from the acids. A perfect example is zinc reacting with hydrochloric acid. Zinc plus hydrochloric acid will only displace the hydrogen from the acid to give us zinc chloride and hydrogen gas, which is, of course, the laboratory preparation of hydrogen by dissolving zinc in a solution of hydrochloric acid. Hydrogen gas is given out. The equation is now balanced. Let's put two here to balance it out. So this is a reactive metal. You have seen that it displaces, that is, it removes hydrogen from this acid. That is what happened is saying that some reactive metals can displace hydrogen from acids. That happens with metals. Non-metal cannot do that. Non-metals cannot displace hydrogen from acids. Okay? And then the last one, metals generally form ionic compounds, while non-metals form covalent compounds. Now, what is the difference between that? To explain the difference between ionic compound and covalent compound, let's understand what we call electrovalent and covalent. Recall that we said that metals ionizes by losing electron, while non-metal ionizes by gaining electron. Now, when an electron is removed from sodium, for example, to give a sodium ion, and then chlorine accept that electron to become a chloride ion. Now, here there's a total transfer of sodium, total transfer rather of electron from sodium to chlorine, such that because sodium is now positively charged, while chlorine is negatively charged, positive and negative will always attract. That is, unlike charges will always attract. So there is going to be a force of attraction between the ion of sodium and the ion of chlorine. And that force of attraction is a bond between the chloride ion and sodium ion. So this type of bond is what we call ionic bond. Ionic. Because as a result of these two ions, sodium ion and chloride ion. So it is formed by what? A total transfer of electron from one atom to another atom. And that happens only in what? In metals. Because metals will donate electrons, while non-metals will accept the electron. Covalent bond on the other hand, covalent compound is electron sharing. In that case, there's no transfer. This one here, between sodium and chlorine, there's a total transfer. producing ion. The force of attraction between the positive and negative ion forms a bond called ionic bond. For covalent, there is a sharing of electrons. For example, carbon has 4 electrons in the outer shell, while hydrogen has only 1 electron in the outer shell. For a bond to be formed between both of them are non-metal. For a bond to be formed between carbon and hydrogen, no, carbon is not willing to lose any electron. As a matter of fact, it's a non-metal. It doesn't use it, only accepts. Hydrogen is also a non-metal. It doesn't use, it accepts. So both of them, for a bond to be formed between them, instead of a transfer of electron from one atom to another, there's going to be a sharing of electron. That type of bond that is formed as a result of sharing of electron between the atoms involved is a covalent bond, and the compound is a covalent compound. So why metals forms ionic compound, no metals form covalent compound between themselves. That is what that point is talking about. So the differences between metals and non-metals. Okay, so because that, we say that matter can be classified or mixture. So with covered element, we say that is a substance by ordinary mix. Then we also look at the classes of elements. We said they could be metals, non-metals, or metalloids. And we look at differences between metals and non-metals in terms of their physical properties and chemical properties. Then we also look at metalloids, which we share the properties of metals and non-metals. So now let's move on to another classes of matter, which is compound. What is a compound? A compound is a substance that contains two or more elements that are chemically combined together. The key word here is chemically combined together. Why do I say that is a key word? Because you may combine two or more things and then those things are not chemically combined. When we say things are chemically combined, that means there's a reaction between them to produce a new substance that is totally different from the substances that you combine. So once that happens, then you can say that the substances are chemically combined. So a compound is what? A substance that contains two or more elements that are chemically combined together. And a compound is formed as a result of a chemical change. In other words, a new substance is formed, a new substance that is entirely different from its form. The components element of a given compound are always present in a fixed ratio by mass. What do I mean? As long as it is a compound made up of two or more elements, the ratio is always fixed. The ratio is what fixed. For example, water is a compound. For water to be formed, there has to be a reaction between two elements. And the elements are what? Hydrogen and oxygen to give us water. To balance this equation, that I have two hydrogen here, I have two here, two oxygen here, but one here. So I will put two here to balance the oxygen. By putting two to balance the oxygen, the two also affect hydrogen times two, which makes hydrogen to be four here. To balance it, I'll have to put two here also, so that the reaction balances. So you can see here, for water to be formed, we need 2 moles of hydrogen to 1 mole of oxygen. That is what that point is saying. The component elements of a given compound are always present in a fixed ratio by mass. Go to anywhere in the world, as long as it is water, the component is 2 moles of hydrogen to 1 mole of oxygen. That is what that point is saying. That the component of a compound are always present in fixed ratio by mass. Carbon dioxide also CO2. Look at it. Carbon plus oxygen to give us carbon dioxide or carbon dioxide. Now, on the left hand side, we have one atom or one molecule of carbon. On the right hand side, also one. On the left hand side, one oxygen. On the right hand side, sorry, on the left hand side, two atoms of oxygen. Right hand side, two atoms of oxygen, which means the equation is balanced. So here we have what? 1 mole of carbon to 1 mole of oxygen, or one atom of carbon to two atoms of oxygen. So again, that is a fixed ratio by mass 1 to 1 in this case. So since the components of a compound are always present in fixed ratio balance, we can represent a compound with a chemical formula, unlike mixture that cannot be represented by a chemical formula because there is no reaction between the mixture. For example, if you have kerosene and water or kerosene and engine oil, there is no reaction between the two. No new substance is formed. So we cannot represent them with a chemical formula because the mixture is not present in fixed ratio balance. So we have some common examples of compound, their constituent elements, and their formula on this table here. Water is the first one here, which I already talked about in this example, because here for water to be formed, you need 2 moles of hydrogen to 1 mole of oxygen. That is a fixed ratio by mass. So we can represent water with what? The chemical formula. The chemical formula of water is H2O. The component elements are hydrogen and oxygen. Also, sand is a compound. Sand is made up of silicon and oxygen present in fixed ratio by mass. 1 mole of silicon to 1 mole of oxygen, or 1 atom of silicon to 2 atoms of oxygen. So the chemical formula for sand is Si for silicon, and O2. That is a chemical formula for sand. SiO2. And limestone, the component elements are calcium, carbon, and oxygen present in fixed ratio balance. And as long as it is in fixed ratio balance, then we can represent it with a chemical formula. So the chemical formula for limestone is CaCO3 as calcium triisocarbonate 4, or simply put calcium carbonate, the old name. There's what we call old name and IUPAC name, which we'll cover later. So I mentioned 2 names here. I say calcium triisocarbonate 4 or calcium carbonate. The calcium triisocarbonate 4 is the IUPAC name, while calcium carbonate is the old name. More on that later. Now, we also have common salt, which is also a compound, that is the table salt that we eat every day. And the component elements are sodium and chlorine. Again, because they are present in fixed ratio by mass, we have a chemical formula for it. And the chemical formula for common salt or table salt is NaCl. That is Na for sodium, Cl for chlorine. And another example is sugar. Now, when we say sugar, sugar chemistry, you know, that sweetener that we use to sweeten our tea or our curry or whatever. That is just an example of sugar. There are several sugar in chemistry, one of which is glucose. We also have fructose, we have sucrose, even carbohydrate that we eat is also sugar, complex sugar. So when I say sugar here, it's not only the sweetener used for sweetening drinks. So we can say I have sugar in bracket glucose. The component element are carbon, hydrogen, and oxygen. And these 3 elements are present in fixed ratio by mass. So we can represent sugar with a chemical formula. The sugar in this case is glucose, which is C6H12 and O6 is the formula for glucose. There's 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. Then ethanol, also a compound. The component elements are carbon, hydrogen, and oxygen, present in fixed ratio by mass. As such, you can represent it with the chemical formula. And so the formula is C2H5OH. There's 2 atoms of carbon, 5 atoms of hydrogen. Then there's a group here which we call the hydroxyl group, which is a functional group of ethanol. We'll talk about this when we come to organic chemistry. Okay? Then washing soda, also another example of compound. The component elements is sodium, carbon, hydrogen, and oxygen, present in fixed ratio by mass. Formula is NaCO3 dot 10H2O is a hydrated salt. That is sodium triisocarbonate 4 decahydrate. Deca, that is 10 moles of water of hydration. We talk about this when we come to salts. Then another example of compound, common compound that we make use of every day is soap. And the component element is sodium, hydrogen, carbon, and oxygen. And the formula is C17 complex H35 and COONA. That is 7 out of 17 other atoms of carbon, 35 atoms of hydrogen. Then this is a group, a carbonyl group. Then the sodium ion attached to it, sodium atom, right? Then lastly, we have caustic soda. The component elements are sodium, oxygen, hydrogen, also present in fixed ratio by mass. And so this formula is NaOH, one atom of sodium, one atom of oxygen, one atom of hydrogen. Or if we look at it in terms of group, it is a hydroxyl group. Okay, so that is that for compound. Another classes of matter. Because we say matter is classified into three elements: compound and mixture. It is mixture. What is a mixture? A mixture is a substance that contains two or more substances that are not chemically combined. That is just the difference between a mixture and a compound. For a mixture, there is no chemical reaction between the components, and the components are not in fixed ratio by mass. While for a compound, there is a chemical reaction between the components to produce a new substance that is entirely different from the component element. Hmm? That is a different. For mixture, there is no chemical reaction. And for compound also, the combination is between elements, two or more elements that are chemically combined to form a new thing with properties entirely different from the element that combined. Here, for mixture, it could be mixture of elements, it could be mixture of compound that are not chemically combined. Like the example I give earlier, a mixture of oil and water, oil and water, or kerosene and water. This is a mixture of compound and the mixture itself. Mixture kerosene is a mixture of hydrocarbon. The mixture plus water, giving us a mixture. There's no chemical reaction between kerosene and water. And so the product is still a mixture. So once there's no reaction between the components that you put together, the product will be a mixture. And because they are not present in fixed ratio by mass, we cannot represent such with a formula. So there is no chemical formula for mixture. Also, we cannot represent it with a chemical equation. For example, when we talk about hydrogen combining with oxygen to give us water, this is a chemical equation. For mixture, we cannot have this type of chemical equation. As a matter of fact, there is no formula for kerosene because kerosene itself is a mixture of hydrocarbon. So there's no way I can write a chemical equation for mixing kerosene with water. Kerosene plus water to give us a mixture of kerosene and water. This is just illustration. This is not a chemical equation because there's no chemical formula here. Also, there's no chemical formula. Unlike this is a chemical formula. This is a symbol of chemical symbol of an element. This is also a chemical symbol of an element. So the point I'm trying to bring out of here is mixtures, the components are not chemically combined and we cannot represent them with a chemical equation. Also, the components are not present in fixed ratio by mass, and so there's no chemical formula for a mixture. A perfect example is kerosene. I love using this as an example because a student actually asked me in one of the classes that what is the chemical formula for kerosene? And I told him kerosene is a mixture, not a compound, and so it doesn't have a chemical formula. The same thing applies to petrol engineering. Let's get some example first. We have some common examples of mixtures here and their component. The first one is air. Air. Air is made up of different elements. And these elements are not chemically combined, and so that makes air a mixture. And what are those elements? You have oxygen, you have carbon dioxide or carbon dioxide, you have nitrogen, you have rare gases, dust, and moisture. All of these are present in the air. Now, different elements and some other things present, but because there is no chemical reaction between them, so that makes air a mixture, and we cannot write a formula for that since the components are present in different ratio by not a fixed ratio by not. Now, Another example is soil. Soil. Now, when we say that in this example of compound, now we're talking about mixture, soil. What is the difference between soil and sand? If sand is compound, why is soil mixture? The difference is that sand is made up of two elements that are chemically combined. There is the element of silicon and oxygen. There's a chemical reaction between the two to give us what? Silicon oxide, which is called sand in our everyday conversation. Soil is a mixture of sand and some every other things like clay, humus, water, mineral salts, and air. That is the meaning of soil. So soil and sand are not the same thing. Soil is what? Made up of sand itself plus dead organic matter, which we call humus. That's dead plant and animals. That's decayed humus plus air plus mineral salt and other mineral resources. The combination of all of this is what we call soil. So soil is a mixture of all of this. They are not chemically combined. Then you have urine. Urine is made up of urea, it's made up of water, it's made up of mineral salts. All of these are not chemically combined. And so urine is a mixture. We also have all not only Coca-Cola, all those sweet carbonated drink, even beer and all of that. They are mixtures of different things. Wine, milk, seawater. Good. I love this example, seawater. We said earlier that water is a compound. Under examples of compound, 32. This is talking about pure water now. When I say pure water, to a Nigerian listening to me, it's not the sachet water we drink I'm talking about. I'm talking about water that is free from any other thing. That is what I mean by pure water. That nonsense we drink and call pure water, there's nothing pure in it. It's just a packaged water. Okay? So the pure water I'm talking about, that means water that is not diluted by anything. Is that type of water classified as a compound and is made up of hydrogen and oxygen in the ratio of 2 to 1. That is a compound. But I'm talking about seawater. Seawater is made up of different things. The water itself, the mineral salts, the bacteria, the remnants of organic matter, that is dead organic matter. As a matter of fact, you have a lot of salt in seawater. So you cannot say seawater is a compound. And now that salt is not chemically combined with the water. You can easily separate the salt from water by evaporating the water. So seawater is a mixture, not a compound. Then blood is also a mixture containing water, protein, fat, oil, sugar, mineral salts, vitamins, hormones, enzymes, blood cells, and hemoglobin. All of these are components of blood, and because they are not chemically combined, that make blood a mixture. Then crude oil, which is made up of petrol, heavy oil, gas oil, kerosene, naphtha, bitumen or bitumen, whatever they call it, gas, all of these are not chemically combined. And so crude oil is a mixture, not a compound. Then lastly, brass. Brass is an alloy of copper and zinc. The copper and zinc are not chemically combined. Yeah, even though the two of them are elements, copper plus zinc, there's no reaction between them. And so what you have is an alloy of metal, which we call brass. But there's no any reaction between them. We see it as a mixture of two elements. Differences between mixtures and compound. A mixture may be homogeneous or heterogeneous. Why a compound is always homogeneous? When you say something is homogeneous if the components are such that you cannot identify one from the other. What do I mean? If I dissolve salt, salt plus solution. As a matter of fact, once the salt dissolves completely, if you look at the water, there's no way you can identify the salt from the water. In short, you won't know that there's salt in the water unless you test it. So even though there are two things in that water, the water itself and the salt, but they have mixed together completely in a way that you cannot identify one from the other. Such a thing is described as homogeneous. Homo means the same. Genus means homogeneous. That is, the components are blended together in a way that you cannot distinguish one from the other. A good example is milk. Now, when you buy a cup of milk, the liquid milk, Yeah, even though this milk is made up of different things, there's no way you can identify those different things. You say, okay, this is mineral salt in that milk, mineral, or this is sugar, or this is whatever, all the components. The same thing, like the example I gave here. But if you have a mixture of, say, let me use a very typical example. Maybe you just put a cup of rice and beans together. Of course, you can easily identify the rice from the beans. So that type of mixture where you can identify the components easily is heterogeneous. Why the one you cannot identify the component is homogeneous. So in essence, a mixture may be homogeneous. That is a situation where you cannot identify the component, or heterogeneous, like the mixture of rice and bean, you can identify the component. Compound is always homogeneous because once it is a compound, remember that new substance is formed from the component that combined. That new substance that is formed is entirely different from the component element. And so the components are homogeneous. You cannot identify one from the other. Then, number two, the constituents are not chemically combined. That's for mixture. The constituents of mixtures are not chemically combined. Therefore, mixture can easily be separated and recovered by physical means. For example, this mixture of salt and water can be separated by using evaporation. You just need to evaporate the water to dryness, and then I recover my salt. You can't do that with the compound because the constituents are chemically combined together. Therefore, they cannot be separated by physical means. Then the third one, so the constituent can be added together in any ratio by mass. Hence, we cannot represent a mixture by a chemical formula. Why for cost? Chemical formula. And the last one, the properties of mixture are the sum of the individual components. That is, the properties of mixture, the mixture that is obtained, is not different from the individual component that form the mixture. That is what they are saying. Why for compound, the property is entirely different from the individual constituents that form that compound. So that is the differences between compound and mixture. In summary, the topic is classification of matter. And we say that matter is classified into three, which are elements, compound, and mixture. Element is what? A substance that cannot be split into simpler units by ordinary physical means. Again, it is classified into three. You have metals, you have non-metals, and you have metalloids. Then we say metals are elements that ionize by what? Losing electrons. Why non-metal ionize by gaining electrons? Metalloids share both properties of metals and non-metals. Then we come to compound. So a compound is a substance that contains two or more elements chemically combined together. Two or more elements, that is element A plus element B, that react chemically to form from the element that combined. It's a compound. And because the element combined are always present in fixed ratio by mass, then we can represent the compound with a chemical formula, unlike mixture, where the components are not present in fixed ratio by mass. Hence, we cannot represent mixture by a chemical formula. That brings us to the end of this.